Let us now return to the problems that I had shown earlier about probabilities and our intuitions. So in this case, we saw that we had tossed a fair coin 10 times, and every time it had come up heads. So we've got 10 consecutive heads. So what is the probability of getting a tail on the 11th try? Now, many people would think that the probability of it coming up tail on the 11th try is now higher than 0.5. Why? Because heads and tails are supposed to be equally likely. Heads has turned up so many times, so it's about time that a tail turned up, right? And a lot of people who gamble obviously fall prey to this misconception. In reality, of course, it's a fair coin, and of course, the fair or not doesn't matter. But every toss of the coin has no impact on any subsequent tosses, right? Each toss is completely independent, and therefore the probability of getting a head or a tail doesn't change, right? Whether it's a fair coin or unfair coin, that doesn't matter. That probability does not change, even though whatever events may have happened in the past, okay? Because all these events are independent. So that's one kind of common misconception that people have about this problem, where if you consider all families that have 4 children, then what is the likelihood, or what is the most common or expected distribution of children of each gender? Now, most people would justifiably think that 2 boys and 2 girls would be the most common distribution among families with 4 children. That is actually not true, because in reality, having 3 boys and 1 girl, or 3 girls and 1 boy, that has a probability of 0.5, whereas probability of having 2 boys and 2 girls is only 0.375. Okay, obviously this probability is higher because it can happen in 2 ways, right? This encompasses you having 3 girls or 3 boys, which is much higher than just having 2 girls and 2 boys. This can happen in only one way. That can happen in 2 different divisions, right? Which we tend to miss. So this is another common misconception that people have about probabilities. A third thing, of course, was our question about Linda and the bank teller, Linda the bank teller, right? So we said from the description, we see that Linda is a person who is highly concerned with issues of discrimination, justice, equality, and participated in anti-nuclear demonstrations and so on. And then we asked the question, which is more probable, that Linda is a bank teller, and Linda is a bank teller and is active in the feminist movement? Quite a few people tend to pick option B, right? Because of this graphic description of her involvement in all kinds of social causes. And this obviously is connected to that. So we tend to relate these two and choose option B, whereas obviously option B is a more restrictive option than option A, right? In order to satisfy option A, all she has to be is a bank teller. For B, she has to be a bank teller and then something else, right? So this is a combination of 2 events, A and B, whereas this is just A. And this is obviously going to be smaller than this because this is a subset of this, right? That is, bank tellers who are active in the feminist movement is a subset of all bank tellers, and therefore the number of people in this class is smaller than the number of people in this class, and therefore the probability of A is actually higher, whereas quite a few people end up choosing B. Okay, so the point of all of this is that our intuitions when it comes to probability can quite often mislead us, except in the most simple, trivial kind of scenarios. So I thought it's a good idea for us to use the naive Bayes unit to also talk about probabilities and look at some of these issues. Although, of course, these may not be directly relevant to the topic of naive Bayes, but I'm just using the opportunity to talk a little bit about probability.